Good morning, everybody. All right, we're going to continue on today with our exploration of. We talked about kind of electrons, right? We started talking about how to deal with the kind of electron configuration with an atom. We saw that atoms kind of will hang out in orbitals. Orbitals with different shapes, and they will always kind of occupy the lowest energy orbitals first, and then they're going to start kind of occupying higher and higher ones as the lower ones get filled up. So we saw last time that we could get the electron configuration essentially from the periodic table, though we did learn a couple of tricks to kind of go past that a little bit. So I want to just make a distinction. I think last time we did we do iodine maybe? Let's see. Iodine, if we look on the periodic table, excuse me. Oh no, my periodic table's not open. If you look at iodine, oh, I chose the wrong noble gas. It's here number 53. We should have chosen krypton. If we want to look at what iodine's electron configuration was, we could say it's krypton, followed by 5s, 2. Then we've got 4d here in the orange, and then we've got, in this colorful part, we've got the p electrons, so we have 5p there, 5p5. So wrong noble gas, but okay. We saw we had 5s2, 4d10, 5p5. And yesterday I kind of made, not yesterday, Tuesday, I kind of made the declaration that most of the chemistry that we deal with is in regards to the electrons that are in s and p orbitals. And I think more specifically, we're looking at ones in kind of the higher s and p orbitals. So with that, we call those valence electrons. And those electrons we are going to call are, they're located in the highest energy orbitals. So valence electrons are located within their highest energy orbitals in a given atom. And the highest energy ones, we're going to see that we kind of make this more specific by really only talk about s and p orbitals only in your highest shell. So d electrons, we're going to see, because they are of a lower shell, even though they're still kind of higher energy electrons, those d electrons don't really do much. They're kind of still buried underneath all of these outer ones, and so it's harder for them to get out and interact with different things. So typically when we talk about valence electrons, we really only mean the ones that are in the highest shell, the ones that have the largest number in front of them. And so, if we were to look at the valence electrons here on iodine, we would see that it would be those two. The electrons in 5s and 5p for iodine would be its valence electrons. And so iodine has a total of 7 valence electrons. And those are the ones in the s and p orbitals in their highest shell. So for iodine, that's shell 5. And the s and p orbitals, we'll count all the electrons there. So we have 2 in s, 5 in p. Putting those together, that's 7. If we take a look at another one, so boron was helium, 2s2, 2p1. we would say boron has 3 valence electrons. So, big thing for valence is we're dealing with s and p orbitals only in the highest shell. So whatever your highest shell is for your atom, it's always going to be after your noble gas configuration, if you're doing a noble gas configuration, or it's just the highest number shell. Anything in s and p for those will be considered a valence electron. We're going to see that all other electrons within an atom they're called core electrons. And those electrons are called core electrons because they're closer to the nucleus, right? They're within the atom more, closer to its core, and so we call those core electrons. And those essentially don't do much. It's hard to get core electrons to react. You got to really zap them with X-rays and things to get core electrons to start moving. That is, moving away from the atom. So typically when we talk about electrons in general, we make those two distinctions: valence electrons, which are in the outermost orbitals, s and p orbitals only, and everything else. And the first category is called valence. Maximum you can have a valence electrons is 8, by the way, because s and p hold 2 and 6. So add those up, that would be 8, the maximum. Your core electrons is everything else. So everything in the d orbitals, the f orbitals, and then all the things covered by your noble gas kind of shortcut. Those are all core electrons, which, as we're going to see, don't really do much. So that's kind of our classification of electrons there. So if we are looking at iodine again, we saw that iodine, it has 53 total electrons, right? We saw that on the periodic table. We saw it has 7 valence electrons. And so therefore, because 7 of them are valence, the other 46 of them would be core electrons. So your valence electrons are one set, one category. Everything else is core electrons. And so again, you get this from your, you can get it from calculating how many are in your s and p orbitals of your highest shell, or we can actually look at the periodic table. We're going to see we have some tricks for ourselves. If we're looking at things in just s and p orbitals, we're going to see that we can just follow the periodic table. And so we can say everything in these columns has that number of valence electrons, right? Because this would be, for example, 4s1, 4s2, 4p1, 4p2, 4p3, 4p4, 4p5, 4p6. So if you're looking at something like this thing here, whichever I think maybe arsenic, it's 4p3, so it's got 4s2 and 4p3. So it has 5 total valence electrons. So that's where this number comes from. We have to add our s electrons and our p electrons of our highest shell. And so if that's the 4th shell, as in the case with whatever that element is, I think it's arsenic, we will see that that the numbers will add up kind of with these columns. So if you're ever asked, how many valence electrons does something have, your options are between 1 and 8. for our neutral atom, and you're going to see that things are going to follow these categories. If you think about the D block, oh, that's so ugly. These also only have 2 valence electrons. Because we don't add any p orbitals in the D block, we're still stuck with our s orbitals. So something like iron here, if we do iron's electron configuration, 26, so 1, 2, 3, 4, 5, 6. If we're going to do iron's configuration, let's not do it in orange though. Let's see, we're probably going to have argon 4s2 3d6. That's irons, right? So it's in the D shell, so or D block, so it's the 6th one there, so it's 3d6. Notice that iron has 2 valence electrons. And doesn't matter which one you're looking at, we're going to see that all transition metals have 2 valence electrons, technically speaking. We're going to see that the transition metals will do weird things sometimes. So again, we usually focus more on main group elements in this class, but we'll see some consequences of this in a little bit once we deal with the number of valence electrons. So far so good, I hope. Alrighty then, let's go ahead and sally forth here. If we look at trends in the periodic table, we're going to see some characteristics that we're going to be able to talk about. And kind of the first one I usually like to talk about is atomic size. Or like the radius of an atom. If we consider atoms to be spherical, we can talk about their relative size. And so we're going to see that we can make some comparisons. Perhaps the most easy comparison for us is if we employ this Bohr model. If I say this is hydrogen, lithium, sodium, potassium, there's a pretty obvious trend here in terms of size, even though these are just kind of pictures, right? We see that as we go down the periodic table, we are adding more shells, which means you have a larger atom. And this one's pretty self-explanatory, right? If you like to use this old model of the atom that had circular rings, those rings get bigger because you're adding more and more of them. And so we're going to see that as you go down a group on the periodic table, you're going to be adding more shells to your atom, and therefore your atom will be larger. Simple as that. So as you go down a group, the elements get larger. So, for example, of these ones, we saw that potassium, of these 4, potassium is the largest, and it's also the farthest one down on the periodic table in that group. So we saw here we had hydrogen, lithium, sodium, potassium. So we're going down the group, and we're seeing, I guess that's slightly to the side, but move this one. There we go. Okay, so as we go down the group, hydrogen, lithium, sodium, potassium, we see that potassium was the largest of those. And rubidium would be even bigger, cesium even bigger, and francium would be the biggest. And then whatever this number 119 is, but we'll see if that ever gets discovered. But for now, that's what we're looking at. Okay, let me bring that over just a little bit. Okay. So, let's do that. So as you're going down a group in the periodic table, your elements will get larger. Hopefully that's the easiest part of this. So the biggest kind of thing is shells. The number of shells you have is kind of your biggest indicator of size. Within a period, though, all atoms have the same number of shells, right? But we're going to see that if we take a look at, let's say, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. So this is the second period of the periodic table. If we draw those atoms, I'm going to just draw like 3 of them because I think it'll just be easier to illustrate the point. Maybe best I should have exaggerated this. So if we look at how it happens on the periodic table, if we're going to the right, if we're going from lithium towards neon, we see that the shells stay the same. But as we know, as we are going across the periodic table, we are adding protons to our nucleus, right? And so if you think we have the same number of shells, the same orbits around them, that's not changing, but we are adding more and more protons to our nucleus, right? As we go to, elements are defined by the number of protons, right? Lithium has 3 protons, fluorine has 9. 1, 2, 3, 4, 5. Yes, 9, I think. Yeah. So fluorine's got 9 protons. Neon has 10. We're going to see that because they have the same number of shells, more protons means you have a bigger positive charge in the nucleus. And that means that shells are more attracted to it. Because if you think shells which are filled with electrons are negative. If you have more positives in your nucleus, the shells are going to be more attracted to it, right? And so we're going to see that as a result, the size decreases. The size will decrease across a period. So we're going to see that lithium, I did a terrible job with these drawings, but let's actually just put them as dots. Single dots. I tried to convey more electrons of the nuclei, but we see here that we're going to see as we go to the right on the periodic table, we're increasing the number of protons in our nucleus. That's how we distinguish our elements. And the more protons we have, the stronger our nucleus is in terms of positive charge. And so, because it's positive, electrons in the shells are negative, they're going to be attracted more to a larger positive charge. And so as a result, those shells contract a little bit. So they get closer and closer to the nucleus as a result. And therefore, we can see that size will decrease across a period. So lithium in period 2 is the biggest one. And neon is going to be the smallest. So kind of our first factor here is number of shells. Number of shells will dictate your size. If you have the same number of shells, then we want to see what's called your effective nuclear charge. That's what this is called. Which is abbreviated ZF. Your effective nuclear charge is effectively your charge in the nucleus. So the bigger your charge is, because you have more protons, as you move across the periodic table, we're going to have the electron shells contracting, getting closer to it, thereby decreasing the size of the atom. And so we see here that that size decreases. And so if you want to put these two trends together, here are just some elements. We're going to see that the size increases if we go the opposite way. So as we go left along the periodic table, our size increases because we have lower effective nuclear charge, so our shells are farther out. And then the more shells we have, that's also going to increase our size. So we're going to see that francium is our largest element, and helium is our smallest element. And they're on opposite corners of the periodic table, right? Helium is in the top right, the smallest one, and francium is the largest in the bottom left. So that's what we're looking at with these. So by understanding these trends, we can make some predictions about things. We can talk about oxygen versus sulfur, sulfur versus selenium, sulfur versus phosphorus. If you can locate these things in the periodic table and apply their trends, that's what I'm looking for. So of the following, which has the largest radius? So I might ask you something like this. Of the following, which of these has the largest radius? And in order to answer this question, we're going to first need to find all these on the periodic table. So if we do that, iron is somewhere here. Let's see. Sulfur is here. Selenium is here. So the more kind of familiar you are with your periodic table, the better. But that's part of this. By looking these things up, you're going to become more familiar with it. And then rubidium is over here. And so if we're looking at what's got the largest radius, That means the biggest atom. We're looking for the thing closest to the bottom left. And of all of these, we'll say, well, that's rubidium. Because rubidium is farthest to the bottom left. So it's farthest to the left, it's also farthest down. And so rubidium will be our answer. And if we were to look at the smallest one, that would be sulfur here, because it's the farthest to the top right. If we're comparing these four. Sulfur will be our smallest of those four. Alrighty. Cool. Alright, we've got a couple more trends to talk about. Metallic character. How metallic is something. Metallic properties we talked about, shininess and silvery and hard and tend to lose electrons and conductive and all those fun things. This trend is already one we probably have in our minds. Remember, these were nonmetals. And these were metals. And along that zigzag, we have some metalloids, right? And so, if we're looking at the periodic table, and we just want to guess, it's looking like the same kind of trend, right? We see as we go left and down, we're looking more metallic than if we go to the right and up, right? We see that the non-metals are here. They're all the way on the right, and they are more on the up side of things. And the metals are everything else. And we're going to see, therefore, the trend is the same as size. We're going to see as we go left across the periodic table, and as we go down. So we would say that, again, francium is our most metallic element. And remember, so that means not only physical properties, but chemical properties too. So it's going to have a tendency to lose electrons in reactions. It's going to be kind of shiny and silvery, and all those characteristics. And we're going to see that, again, helium is our least metallic element. And if we think of helium, probably think of balloons. Are we filling our balloons with metals? Probably not, right? So, I mean, just kind of, we already have this idea in our head. And so we're going to see that kind of the more we go left, the more metallic we get. As we go from stuff like nitrogen and oxygen, which are gases, to things like lithium, which is a metal, silvery metal, metallic, shiny. And as we go down, as we start with carbon, which is charcoal, we go to silicon. Silicon is kind of semi-metallic. It looks like a metal, but it kind of feels like a non-metal. And as we keep going down, we get to lead. Lead, we know, is a metal, right? It's what causes all those problems, but it's definitely a metal. And so as a result here, we're going to see that it's the same trend as size. So francium is your most metallic, bottom left. Helium is your least metallic, top right. All right, so hopefully not too bad there. hopefully. Okay, let's go ahead and take a look at the next little bit here, our next trend. So if we were to look at these last ones, we would say that rubidium is our most metallic element and sulfur would be our least metallic if we were looking at the same ones. So, exciting. The last one is one that maybe is a little less obvious in terms of its kind of words. Its words are a little bit harder for us to deal with. And so, with these, I better define it, huh? This is the amount of energy required to lose one electron from an atom. So it's an amount of energy required to lose an electron. So there's always an energy loss. It takes energy. It's an endothermic process to lose an electron. So we're going to see here that some elements will have low ionization energies, and some will have higher ones. And we're going to see that a low ionization energy means that it's easy to lose the electron, and a high ionization energy means it's hard to lose electrons. We could also say that this means that these electrons are kind of loosely held, and these electrons are tightly held. I'll give you a second to write that down. Oops. So we're going to see here, with knowing our previous trends, we can kind of make some predictions about ionization energy as well. So if we were to think about electrons that are loosely held, it may be a good idea to revisit size or metallic character. If we look at size, if we're comparing two elements, if we say are comparing lithium and fluorine, visually we might be able to see this as well. We might be able to say, okay, maybe one of these looks more like it's tightly holding on to its electrons and hoarding them, and maybe the other one kind of just doesn't care about that electron out there. May have given it away, but we're going to see that because fluorine had the greater effective nuclear charge, remember the shells are closer to the nucleus, and that means that we have tightly held electrons. On the other hand, this lithium, that electron is really far away from the nucleus. This electron is far from the positive nucleus, nucleus apparently, and so it is loosely held. And so as a result, we're going to expect that this one would have a high ionization energy and this one would have a low ionization energy. It's easy to remove the electron if it's loosely held. If it's far away from the nucleus, it's like, okay, I'll go out. I'll go do something else. But the ones in fluorine, it's going to be pretty hard to take one off because those are all really close to the nucleus, and so they're much more tightly held onto. So it's a lot harder to remove an electron because they're much closer to the nucleus, which is more positively charged. Alrighty. If we want to think about this instead, in terms of metallic character, we see that, for example, if we compare lithium, actually, sorry, let's do size again. Use lithium and potassium now. If we were to go and steal one of these electrons, if we wanted to, we're going to see that this electron is even farther away. And therefore, it's even easier to take. So this electron out here is even easier to take away than the one in lithium. And so, as a result, what we're looking at here is that potassium is going to have a lower ionization energy than lithium will. It'll be easier to remove that electron from potassium, and as a result, because it's easier to remove, it has got a lower ionization energy. And so the trend for this will, depending on how we want to talk about it, we're still looking at kind of the same extremes. We're still comparing helium and francium there. So francium is going to have our lowest one. So if we're looking at ionization energy, it increases as we go up and to the right. So as we go farther up and to the right of our periodic table, we're going to see that things will get higher and higher in terms of their ionization energy. So we'll kind of go from there. If we want to think about metallic character, we saw that francium is the most metallic. One of the characteristics of metals is that they're likely to lose electrons. And so if they're going to lose their electrons more easily, being more metallic, that means that they have relatively low ionization energy. And so it's the same kind of trend there as we go across. We can see patterns in all of this stuff. Patterns, patterns, patterns. That's all this is. All right. Shall we see the purpose of this? Well, I mean, these patterns are a little bit less purposeful, perhaps. A little bit more important later on. We talk about the size and all that. But these are the trends. Okay, so those are kind of periodic table wide trends. If we're looking at trends within a group, if we take our alkali metals, say lithium, sodium, potassium, if we just jot down their electron configurations very quickly. Argon. Notice that these have very similar configurations. And they have the same number of valence electrons. We're going to see that anything within a group is going to have essentially the same configuration, just maybe different shells involved. If we look at, say, the halogens, if we look at fluorine, chlorine, bromine, we can look at those. We're going to see that those also will have very similar electron configurations. Fluorines would be helium 2s2 2p5. Chlorine would have neon 3s2 3p5, and then bromine 4p5. These have also very similar electron configurations, right? Bromine has quite a bit more electrons because it's got some in the D block now, but remember that the D block electrons don't really count because they're core electrons. Most of chemistry happens in valence electrons. So these also have very similar configurations. And these electron configurations are going to determine some behavioral patterns that we're going to see. If we take a look at the noble gases, I'm sorry, that's 1s2. Neon, argon, krypton, xenon, why not? Actually, helium's a bad example. I'm just going to get rid of it here. Oh, go away. 2s2 2p6. Argon is 3s2 3p6. 4s2 4p6. And xenon 5s2 4d10 5p6. We see that all these have their full p shells, right? We talked about that when we were determining the noble gas shortcuts, right? So these have completely filled their valence shells, right? The s and p orbitals are completely filled in all of these atoms. And these are the noble gases, right? It so happens in chemistry that elements, just like in real life, they want to be noble. They want to become noble gases if they could. And this is kind of our biggest predictor of what ions will form for a given element. Elements will do what they can. They will either gain or lose electrons to try and mimic noble gases. So noble gases kind of set the fashion trends, and everyone else is trying to copy them. And so most elements will gain or lose to mimic a noble gas electron configuration. And we're going to see we can kind of predict what's going to happen. So most elements will gain or lose electrons in order to become a noble gas, at least in terms of their electrons, right? They can't lose protons, can't mess with the nucleus, because then you're not going to be the same element anymore, right? But we know that sodium ions exist, iron ions exist. Oxygen ions exist. Remember, ions deal with gaining or losing charges, right? So we're going to see here that, let's say, sodium, its electron configuration is neon 3s1. Closest noble gases to sodium are neon and argon, right? Neon will be the one before it, argon will be the one after it, so those are the two closest ones. And so sodium is going to try and become one of them. If you remember, I'm going to just cheat here a little bit. I'm just going to say neon's electron configuration is just neon. And argon's electron configuration is neon 3s2, 3p6. And so if you want to think, if sodium is going to want to become one of these two, because these are the closest noble gases to sodium, it's probably more likely that it's easier for it to just lose an electron. If it can get rid of this thing, if it can get rid of that electron, it will become neon's electron configuration. Or it could gain 7 electrons to become argon, which is much less likely, right? So we're going to see here that for sodium, it can either lose 1 electron or gain 7 electrons to try and become a noble gas. And we're going to see indeed it's much easier to lose 1 than to gain 7. It's much easier to just lose an electron. And we're going to see indeed sodium will very often, almost all the time, lose its 1 electron. And so if we kind of look at what that looks like in terms of like a chemical reaction type of thing, sodium will lose an electron and become a sodium ion. And we're going to see that sodium it prefers and always takes a +1 charge when forming an ion. And we're going to see this will be a pattern. We're going to see that, remember we looked at the other configurations of the alkali metals. We saw they all just have 1 valence electron. And so it's easier for all 3 of those to just lose it, and poof, now they're noble gases. And so we're going to see that the alkali metals will preferentially make +1 ions. They're going to lose 1 electron. And we're going to see some more trends here. Got some more trends here. We're going to see that here's our sodium. Nope, that's not our sodium. That's our lithium. I've left out francium apparently. But all of these prefer to make +1 ions. And in reality, we only ever see them with +1 ions. And we're going to see that we're going to be able to predict that things in the second column will also lose their 2 electrons now to try and become a noble gas. So something like magnesium or calcium, those will always form +2 ions. If we go to the other side of the periodic table, if we look at those halogens, sorry, that's totally not the halogens. There they are. Those halogens are 1 electron away from becoming noble gases, right? If we look at fluorine and neon, fluorine is 2s2 2p5, neon is 2s2 2p6. It's 1 electron away. So fluorine has the option of gaining 1 or losing 7 to become a noble gas. And so, of course, these ones are just going to gain an electron. And so we're going to see that halogens tend to gain 1 electron, making them -1 ions. So their charge will be -1 because they're gaining 1 electron. Remember, adding more electrons, you're adding more negative things, so overall you become negative. And so something like fluorine, chlorine, bromine, iodine, those all prefer to take the charge of -1 when they are forming ions. And if we continue the trend, we essentially will see that all of these kind of patterns will carry through. Noble gases, of course, will never make ions because they're already noble gases. They don't need to react, and that's why they don't react, is because they already have happy electron shells. So electrons are kind of, I mean, I hate to make this anthropomorphic, but they are happy when they are completely filled. So once an electron has a completely filled set of orbitals, it's happy. Or if it's got a completely empty set of orbitals, it's happy. It just doesn't like being in between. And so, as a result here, we see these patterns of preferred charges. And there are a couple more that we will need to know as well. So you will need to know these preferred charges for anything in the groups that they're listed in. So, I mean, I haven't written out everything. I have not written out barium and strontium in the +2 column, but those will still be +2. So everything in these columns will take those charges, preferentially. So much so that they don't make other charges. We're going to see aluminum how do I want to do this? There are a couple of other elements that have preferred charges. These three here. We're not going to have total patterns for them because these are kind of special cases. Aluminum will only ever make 3+. Zinc and cadmium only ever make 2+. And silver only makes 1+. So these are the ones you're going to need to commit to memory. And that will very, very much help you out when we talk about naming ionic compounds. And so with this, everything in these groups that I've listed takes the same charge. So, if we want to guess what barium's charge will be, barium is in group 2. It's in the +2 column. So barium will always take a charge of +2. Everything in the -2 column will take a -2 charge. So selenium, which is in the -2 column, group 6, will always take -2. So with these, it doesn't matter if I've not written them here, but those are the groups you'll need to know, as well as these 4 extra atoms: aluminum, zinc, cadmium, and silver. You will want to know all these preferred charges by memory. And I get it, that's not the easiest thing to do. One more special one is hydrogen. Hydrogen having only 1 electron, it is equally distant from being no electrons or having a complete set. And so we see that hydrogen will either form +1 or -1. Kind of is a special one. So hydrogen is a special element. It can take both charges, either +1 or -1. Even though it's in the +1 column, remember that hydrogen is still a non-metal, right? We see that hydrogen is a gas, right? It's non-metallic. It can either make the positive or negative ions. Generally, it's more stable as the positive one, but it is often seen as -1 as well. So hydrogen is a little bit special. All right, I'll just go ahead and fill these in because it's bugging me. There we go. So you'll want to have learned all of these. I'll write them all out. Everything here you will want to know. That's written out here. You'll want to know, as well as the fact that hydrogen can do either one, +1 or -1. Those are trends that you will need to know. Again, the earlier you learn these, the better. So, okay. So cool. You might be asking yourself now, well, what the heck with these transition metals? And what the heck indeed? We see that transition metals they can take a number of what are called oxidation states. Or we might call them charges. So for example, iron often is seen as +2 or +3, but it can do other things. It can also do +6. No problem. Manganese often takes these. You don't need to memorize these because they can do all sorts of different things. A lot of them can do +2, +3. Some are happy to go way higher. Chromium, 3, 6, 7. All sorts of different charges you can possibly get with chromium. There's not really patterns. Chromium you could also get +2. So, I mean, if we take a look at our dear friend, Wikipedia, just showing you some examples. If we look at iron, for example, let me go ahead and swap this over. Here's iron. We see that very often, I mean, it can take all sorts of crazy electron states, but usually we look at the ones in bold. So 2, 3, and 6 are pretty common for iron. They're in bold here. And so if we look at, say, for example, sodium on the other hand, if we look at sodium, we only have 1, and that's +1. It doesn't typically make a -1, that's why it's not in bold here. +1. So sodium has only got 1, but we saw that iron had all those. Chromium. 2, 3, 6 are the common ones for chromium. So we see all sorts of different things. Apparently I lied to you about 7. I'm going to erase that before anybody notices. But we see here, many different charges are possible for transition metals. Some are more preferred than others. Titanium, 2 and 4, usually. Apparently 3 also. So, all sorts. And indeed, we see that even with some kind of post-transition metals, like lead, it's way over here on the periodic table, so it's after the transition metals. It's in the P block. It's in the 4th group. Has a couple of different ones it takes, 2 and 4. So lead, which we don't have a rule for in our little chart, still takes multiple charges. Okay, and again, indicated in bold here. Let's see, gold. Not gold. I guess I could say AU. Oh, not AUY. Okay, apparently I have to actually go to gold. Okay. If we look at gold, +1, +3 are its most common. So again, all over the place. There is no way for us to kind of make patterns of it right now. Copper, only +1 and +2. Never know. Notice also, so lead, way down here, lead we didn't have a rule for. And we're going to see ones that we don't have rules for often have variable charge. So they have different charges they can take. And I'm just going to erase that. So transition metals can do all sorts of crazy things. We don't have patterns for them. And so, as a result, you're not expected to learn them as such. However, on that, we're going to see, remember I had you start learning your polyatomic ions way back when? If we take a look at that chart again, it's in Discord in our handouts section. Go away. I have listed here common charges. So the main group elements, we have the, oh my gosh, I'm still on, no, I'm not on Wikipedia, okay. Our main group elements, we do have charges. I have common charges listed for some of the variable ones. Common charges. These are not the only ones that these elements can do. If there's only one written, that's the only thing it can do. However, all of these transition metals, look, I've got iron 2 and iron 3 here. We also saw iron does 6 pretty easily. Titanium also does number 3. So don't memorize these transition metal charges that are variable. Those are common charges. Silver, cadmium, zinc, aluminum, yes, you will need to know those, because those are fixed charges. The variable ones you do not need to learn. Also, these names here with it says metals with more ionic charge, you don't have to worry about that. I am phasing this out. It's an old way of talking about these things, and it's kind of less useful. So we see a systematic name is better for those, and we'll learn that. So remember also, don't forget to learn your polyatomic ions. In kind of our next lecture, we're going to need those. So I had asked you, in week 2 or something, we're in week 5 now, to start learning these. So their names and their charges and formulas. So I would get on that. Because if you don't have these, if you have to keep referencing the chart, it's going to really slow you down. You're going to see you have a ton of homework problems with kind of working with these names. So that would behoove you to start learning sooner rather than later. Okay. back to this. So, what to learn? What do we need to learn here? We need to learn preferred charges for the elements in groups 1, 2, 15, 16, and 17. Oh my gosh. Those are the preferred charges. And also for silver, zinc, cadmium, and aluminum. You'll want to learn those as well. Everything else is variable, meaning we do not memorize one charge for all of those. You're also going to want to learn your polyatomic ions. For example, you'll want to learn that this thing is called acetate. And this one is chlorate. And this one is sulfate. You'll want to learn all of these. You want to be able to understand the name and the formula, along with the charge, of any given ion. So these were monoatomic ions at the start here. Mono, one, single atoms. And polyatomic ions, those are the ones on the chart. That chart is in Discord. It's also on Canvas. You'll want to start learning those. All right? We're going to see that we are also going to have names for monoatomic ions, and these names are really easy. These names are sodium ion, barium ion, aluminum ion. Cations are really easy. It's just the name of the element and then the word ion. So for anything fixed charge, with fixed positive charges, it's the element name plus the word ion. Easy. Potassium ion, lithium ion, hydrogen ion. Cool. Great. Nitride ion. Oh no, we're doing positives right now. For negatives, there's only one thing we have, or let's stay with positives for now. For variable charge ones, we just have to say the charge in Roman numerals. So this is a cobalt 2 ion. This one is a cobalt 3 ion. And this is an iron 6 ion. So for variable charge ones, the ion name also includes the charge as part of the name. So cobalt 2, that's written in Roman numerals, has a 2 plus charge. Cobalt 3 has a 3 plus charge. And iron 6 has a 6 plus charge. So we're going to see that for all elements with variable positive charge, It's the element name, and then the charge, and then the word ion. And important to note that charge is written in Roman numerals. And we'll just go over those real quick. So, if you have a fixed charge, it's just sodium ion. That's it, barium ion. They only have one possible charge, silver ion, zinc ion. It's just the name of the element and the word ion. For things with positive charges that are variable, meaning there are multiple possibilities, you say which one you have by putting the charge in the middle of the name. Cobalt 3 ion is cobalt 3 plus. The iron 6 ion is iron 6 plus. Roman numerals we can just go over quickly. All right, so these are our Roman numerals. So in case you need a refresher on those, that's what those are. So something like 4 is written IV. 6 was VI. So just putting those out there in case anybody has forgotten their Roman numerals from, I don't even know, when do we even learn those? Elementary school somewhere, and that it's like forgotten. But I guess if you're a Super Bowl fan or whatever, then you will have seen these Roman numerals every year, right? So, but they're, or like a Final Fantasy fan, I guess you'll see all these as well. But typically we don't really use Roman numerals much either. But, so that's that. The last case is for negative ions. Just so we know, all negative ions are fixed charge. It's just slightly different. So if we have H minus, the way we do this is we kind of lose the last bit of the name. And we have this "ide" ending. So this is the hydride ion. Notice that this one, the positive one, is just the hydrogen ion. For positive things, we don't change the name. For negative ones, we do change the name. This originally is the symbol for oxygen. We're going to kind of essentially take off the last syllable there. And this is the oxide ion. Or here we have chlorine. We're going to get rid of that. Chloride ion. So the pattern here is when you have a negative charged atom, something that has gained electrons, you have this "ide" suffix to indicate that. So we use the "ide" to indicate negatively charged single elements. Some more examples. We have selenium. Again, we are going to lose the last little bit here. And this becomes selenide. So we are kind of changing our ending of our elements to become "ide." I minus, iodine, becomes iodide. when it's negatively charged. All right, and so this is the selenide ion. I need to put the word ion there. And so we include these as part of it. So we're going to see next time, our next lecture will be on naming ionic compounds, which is putting together a positive and a negative ion and having those names put together, like sodium chloride, for example, or calcium fluoride, or barium iodide, or iron 2 oxide. We're going to see that we're just putting the names of the ions with the, or just that's it, without the word ion. So iron 2 ion, oxide ion, put those two together, iron 2 oxide, iron 2 chloride, cobalt 3 bromide. Whatever. It's very simple. We'll also talk about covalent compounds, the compounds that are nonmetals only. We'll see that they have special naming rules. We'll talk about compounds with the hydrogen ion, which gets a little bit more complex. We call those acids. We'll have that as well as a category of naming. And so, it would be a very good idea to learn your preferred charges, as well as to learn the names of these elements and ions, as well as your polyatomic ions. So don't forget those as well. They have their own names. There are some patterns there in the naming. I can show you a bit of trends. I have some trends for you. These have names. These are all on your chart. Some trends for you. There are patterns we see here. So for chlorine, there are 4 different polyatomic ions that we have. Hypochlorite, chlorite, chlorate, perchlorate. All of those, the only thing that's different about them is the number of oxygens that they have. And we see there's a similar trend with sulfate and sulfite. Everything else is the same except for the number of oxygens. So the charge is the same, the leading element is the same. The only thing that changes is the number of oxygens. And so we're going to see that if you memorize the 8s, if you memorize your 8s for ones that have multiples like these, we're going to see that you can kind of deduce the ite form. So if we see that the oxygens will change and nothing else will. So we see that every time we're going from 8 to ite, we lose 1 oxygen, right? So chlorate has 3 oxygens, chlorite has 2 oxygens. Sulfate has 4 oxygens. Sulfite has 3 oxygens. And so this one is nitrate, and nitrite will be exactly the same, but it will lose 1 oxygen. So if you can memorize the 8s of everything, unfortunately, sometimes the 8s can do different things. Like sulfate has 4 oxygens and a -2 charge. Chlorate has 3 oxygens and a -1 charge. Phosphate has 4 oxygens and a -3 charge. So unfortunately, there's no pattern between those But the pattern from ate to ite, from ite to hypoite, is all the same. So phosphite would be the same pattern. We just lose one oxygen, and that's phosphite. So some little tricks to kind of help you learn those polyatomic ions. So if you can put the eights to memory, you can figure out the ites, you can figure out the per-eights and the hypoites just by understanding the patterns in the number of oxygens we have here. So those endings tell us things. Those all have chlor in them, right? Because the chlorine-based ion. But those endings tell us something about the relative number of oxygens. If you memorize the eights, you can figure out the rest of that base compound. All right? So that's what you'll do. Next kind of video we'll have is on putting ionic compounds together. So we'll go from there. All right? Awesome. We'll see y'all next time then. Enjoy your weekends. Take care.